My name is Allison. I know I'm standing between you and your lunchtime, so I'll try to make this short. Today I'll be talking to you about my master's thesis project, which is the timeline of Fatty Acid Incorporation from diet to egg in the California Yellowtail Seriola dorsalis. And this project was in conjunction with Harbor Branch and Hub SeaWorld in San Diego and funded by the USDA. So I know John and Kevin gave a really great introduction of the Seriola genus. So I'm going to give a really quick introduction. So Seriola are a very popular genus in aquaculture, and they are farmed in every continent except Antarctica. Hence the Mr. Worldwide title, if you listen to Pitbull. The most popular Seriola is Seriola kinka, which John talked about, which is mostly farmed in Japan, and it's very popular in Japanese restaurants, and they fetch a really high price. So this picture here is a picture I took from a local seafood market in San Diego, where they were selling a fillet of the local yellowtail for $26.95 a pound. So this is the Seriola species I'll be talking about today, the Seriola dorsalis, or the California yellowtail. They are not yet commercially produced in the United States, but there is a farm in Mexico, and the folks obviously at Hubs has done a lot of research regarding the aquaculture research. There are plans to hopefully open a commercial net pen in San Diego. So one great feature that the yellowtail has as an aquaculture species is that they are very prolific spawners. These fish have very long spawning seasons from March to September, and they can spawn over 200,000 eggs per spawn, and they can spawn every 3 to 15 days without the need for any hormonal induction. So the goal for a lot of broodstock research is to be able to produce high quality and quantity eggs. So for yellowtail, we have the quantity part settled, but what about quality? So we want to be able to produce high quantity and quality consistently. And a lot of broodstock research has already ascertained that a high quality broodstock diet can help to produce high quality eggs. This is because nutrients from the feed are transferred to the eggs through biological mechanisms like vitellogenesis. Eggs depend on nutrients like lipids to fuel activities like hatching. And we see this in a lot of newly hatched larvae where they store high amounts of fatty acids in the yolk sac and oil droplet reserves. However, there is a gap in the research where we don't really know when to start feeding this high quality diet. And identifying this duration will give producers a more precise timeline of when to expect to see changes in egg quality resulting from a diet change. And this information will be very helpful to evaluate potential new feeds for broodstock. So this was our experimental design. We used an alternating diet plan between two diets to evaluate how long it takes for the fatty acids in the diet to show up in the eggs. Each diet was alternated every 41 days, and the experiment was repeated twice. The experiment was conducted at Hub SeaWorld in San Diego from March to September in 2021 during the spawning season. We used F1 generation yellowtail consisting of 3 females and 6 males. They were placed in a flow-through shaded outdoor tank just like the one in this picture. The fish spawned volitionally. Salinity was 34 to 35 parts per thousand, and temperature ranged from 15.9 Celsius to 24.8. So these are the two alternating diets that we used. The cut bait that we used comprised of 70% sardine and 30% squid with an added vitamin premix, and it was fed at 5% total body weight. And for the commercial diet, we used a 22 millimeter Vitalis Prima broodstock pellet from Spreading. Ingredients in this feed include fish meal, fish oil, squid, krill meal, and algae. And this was fed at 1% body weight the amount of each feed was calculated to account for water weight differences. So for every spawn, we collected egg and spawn metrics, which include viability, hatch rate, total eggs, larval length, egg and oil volume, egg and oil diameter, as well as survival to first feeding. We also collected diet and egg samples for each spawn for biochemical analysis, and we analyzed fatty acid and proximate composition. We also quantified polar and neutral lipids for our egg samples. So for our statistical analysis, we grouped our egg data according to two factors, diet and diet duration, which was the duration they were fed the diet. So this figure here shows how the samples were grouped according to the diet duration. So we had 4 interval groups, which were the first 9 days of feeding a specific diet, 10 to 19 days, 20 to 30 days, and 31 to 41 days of the diet being fed. So this allowed comparisons of diet incorporations from 9 to 10 day intervals. We also made the assumption that eggs produced after this 31 days of the diet being fed have already incorporated diet fat. And this assumption was based off of the average spawn interval for yellowtail, which is 2 to 15 days. And spawns should have incorporated diets they were fed by this time. So we used multivariate permanova and two-way ANOVAs to analyze similarities and differences between these groups. So we'll start with our egg and spawn metric results. We had a total of 44 spawn events. Egg and spawn metrics were overall similar throughout the experiment, but we did observe more spawns while being on cut bait. And we think this difference may be caused by seasonal variations because, as you can see, the spawns increased and became more consistent as the season became warmer. Hatch rate, what we also observed was a little bit below average when it should have been ranging from 60 to 75%. Poor hatch rates have been seen in studies where they might have essential fatty acid deficiencies, but they report hatch rates ranging from 6 to 26%. So we think that the large standard deviation that we are seeing here suggests that it may be due to seasonal fluctuation instead. So these are the essential fatty acid results of our different groups where we really saw the significant results. So LNA, LA, and EPA levels were different based on diet type and duration. However, we saw no changes in DHA and ARA throughout our experiment. So I'll be going through how these specific essential fatty acids changed throughout the diet switches. So I'm starting out first with linolenic acid. So this figure shows how LNA, linolenic acid, differed across diet type and duration. This is a piecewise regression model on a scatter plot where each plot represents a spawn. And the x-axis is the aggregate experiment days, and the vertical dotted lines represent when the diet switch occurred. So the left figure shows the neutral FAs, and the right figure shows the polar FAs. Orange is vitalis spawns, and gray is the cut bait spawns. So we observed that there was an increase in LNA in the vitalis spawn. You can see that in both figures, and a decrease in LNA in the cut bait spawns. We observed that the increase from the vitalis diet is seen within 9 days of feeding vitalis. So our next question is, how long can eggs hold on to this higher LNA level after we switch to cut bait? So we observed that eggs selectively retain the LNA levels for up to 19 days after we stop feeding vitalis. And this pattern was also seen in our linoleic acid data, where we saw a clear increase of LA in the vitalis spawns and a decrease in the cut bait spawns. And we found the same selective retention duration of up to 19 days here as well. As for EPA, we kind of saw the opposite, where we can see an obvious increase in EPA in the cut bait spawns and an obvious decrease in the vitalis spawns. And we also saw a selective retention here, where eggs were able to retain this higher EPA levels from the cut bait for up to 30 days after we stop feeding cut bait. As for the overall fatty acid profile, which includes saturated fatty acids, all the monounsaturated fatty acids, and the polyunsaturated fatty acids, we observed the diet type and duration on diet did influence the egg composition. So to illustrate our pairwise permanova results, I made this timeline. The left part of this timeline represent what diet is actually being fed, while the right part represent what diet is actually being incorporated by the eggs. And we saw a lag period from rootstock diet to the eggs, and it was less than 9 days. So although we were feeding Vitalis in the first 9 days, the spawns were more similar to their previous diets, which was cut bait. And after these 9 days, the spawns started to reflect the diet they were actually being provided. And this was the same for our cut bait diet. Spawns fed cut bait for the first 9 days showed similar FA profiles to the Vitalis spawns instead. And after this lag period, they started to reflect their actual diet. So the objective of our study was to determine how long it takes for fatty acids from diet to transfer over to the eggs. Our results show that producers should feed a diet for at least 10 days beforehand to evaluate its influence on egg quality. And this can be applied to other income breeding species with similar spawn intervals to yellowtail. We also found that although yellowtail are income breeders, they're able to retain LNA, LA, and EPA from their previous diets to compensate for future fatty acid deficiencies. And this is an extremely beneficial trait for an aquaculture species, as larvae can be more resilient towards nutritional changes. This was also the first study where Vitalis was fed to yellowtail, and we did achieve comparable egg and spawn metrics to cut bait, marking its potential to actually replace cut bait in yellowtail. So this is it. Thank you for your time and attention. I would like to thank all my committee members, as well as Kevin and Mark and all the hardworking technicians at Hub SeaWorld, and as well as the USDA for funding my portion of this project. It was a really great experience. And thanks, Paul, for being my committee member.
All right, so we have some time for questions, unless everybody really wants lunch. I have a question.
How do you explain the selective retention of all those essential fatty acids in both the neutral?
The question was, how do I explain the selective retention that we see in the polar and neutral fatty acids? That's a really good question. I think evolutionary, if you see in capital breeding species, they have the ability to do that as well, and that's actually really beneficial for larvae to survive. So I think that's like a very natural thing that that larvae are able to do, and it is an expected result that we would get to see like a selective retention. Yes.
When you started this journey, were you interested in a minimum value of these fatty acids getting over into your eggs to ensure hatch success, or were you looking long term maybe to find out what's the minimum value and then to assure some success, and then we're going to try to push that to a maximum and see how far it goes? Or did you ever get to a threshold with that, like there was a maximum and then more was not better?
So the question was there a minimum or a maximum value of fatty acid incorporation we were trying to achieve in the study? That's a really good question. For the study, I think we were just trying to see how long it takes for the fatty acids in the broodstock diet that we are feeding to the fish to be transferred into the eggs. But I think to address that question, you would have to have a longer study because the diet switch only lasted for 41 days. So if you did it for maybe like 2 or 3 months per diet switch, I think you could see like a threshold because the eggs can only absorb like so much fatty acids or carry so much fatty acids. So there is definitely a maximum threshold. But I don't think we achieve that here because I think the diet switch period is way too short to observe that. Because right now, the figures that I saw in my piecewise regression, it went up and down. So I think if we saw the threshold, it would be like up and then a plateau. Yeah, that's a great question. Thank you. Thank you.
All right, well, thank you.